Hello and welcome to DataCast Solutions, Statistics and Data Mining 101 using KNIME. In this chapter we're going to be talking about the neural networks data mining technique. This is going to be one of the longer and more in-depth chapters in this particular class because artificial neural networks are a little difficult to understand. So be patient as we get through it. Artificial neural networks are very popular because they have a proven track record in many data mining applications in use today. Neural networks, we usually drop the word artificial from their name, are a very powerful general purpose tool and readily applied to any type of prediction, classification, or clustering solution that you're looking for. The human brain makes it possible for people to generalize from experience. Computers, on the other hand, usually excel at following explicit instructions over and over again. The appeal of the neural network is that they bridge this gap by modeling the neural connections in the human brain. When you use it in well-defined domains, their ability to generalize and learn from data mimics to a certain degree our own ability to learn from experience. But there is a significant drawback to using neural networks. The resulting trained neural network are a series of internal weights distributed throughout the network, and those weights unfortunately provide no more insight into why the solution is valid than dissecting a human brain would explain a person's thought process. Neural networks are best approached as a black box of internal workings that should be as mysterious as the workings of our brain. Like the response to the oracle at Delphi worshipped by the ancient Greeks, the answers produced by neural networks are often correct. They have business value in most cases. Our more important features have been identified that can be used in exploration. But you're not going to understand how the model made its choice. It's going to be all mathematical. Neural networks actually became popular in the 1980s because of a convergence of a number of factors, including that computer power was becoming readily available. And analysts were very comfortable with neural networks by realizing that they are very closely related to known statistical methods that were proven. And there was relevant data already collected since a lot of operational systems in most companies had already been automated. Because of their proven ability, neural networks are and are going to continue to be a popular data mining tool. Neural networks have the ability to learn by example in much the same way that human experts gain from our own experiences. So the following example I'm going to walk through applies neural networks to solve a very familiar problem with most readers, and that would be real estate appraisal. Now, in this example, this neural network mimics an appraiser who estimates the market value of a house based on features like the property, additional bedrooms, bigger garages, house style, and the size of the lot are factors that figure into her mental calculation. She's not following a known formula, but balancing her experience and knowledge of the sales prices of similar homes. And her knowledge about housing prices is not static. She is aware of recent sale prices from homes throughout the region, and she can recognize trends in prices over time. So she's always fine-tuning her calculation to the latest data. Alright, a tip. Neural networks are really good for predicting and estimation problems. But the problem has to have three good characteristics. The inputs have to be very well understood, and the outputs have to be very well understood, and experience, or in other words a training data set, is readily available. If you've got all three of those, then a neural network is a good model to start with. So the first step in setting up a neural network is to calculate estimating housing values is going to be to set up a list of features that you think affect the sales price. So living space, the size of the garage, all of the types of features, the age of the house and its location, etc., are all going to be input factors, and the output is going to be the appraised value. Training the neural network builds a model which can be used to estimate the target value for unknown examples. Training presents known examples, so in other words, in our case, previous sales, so that the network can learn how to calculate the sales price. The training process internally is adjusting the weights inside to arrive at a combination of weights for making the desired prediction. By reprocessing that training set over and over again and adjusting the internal weights each time to reduce the error, the network gradually does a better and better job of approximating the target values from the training set. In other words, it gets better over time, just like human beings do. All right, perhaps a bit of an overgeneralization, but the inputs to a neural network should be smallish numbers. There are technical reasons for this, however, the inputs are ideally small numbers, like between -1 and 1. This usually requires mapping all the values, both continuous and categorical, to the training network. And so, I've typically used the normalizer on the one-to-many nodes in order to do that. But one way to map continuous values is to turn them into fractions. Another way, mapping the categorical values is to assign fractions between -1 and 1 to each of the categories. Once the idea of the neural network has been trained, the performance of each generation has to be measured on the validation set. So typically early generations of the network perform better on the validation set than on the final data, the testing set. And this is due to overfitting, and that's just a consequence of neural networks being so. So the steps to create a model are going to be the same as you've seen in many other steps like KNN. We're going to identify the input and output features. We're going to transform the inputs and outputs as necessary so that they are in a small range. We're going to set up the network with an appropriate topology. We're going to train the network on a representative set of sample data. Then we're going to use the validation set to choose the right weights that minimize the error. We'll evaluate the network using the test set to see how well it performs, and then we'll apply the model generated to the network against the test file. One of the biggest problems with any predictive model or classification model that you build is it becomes stale over time, like a banana on the shelf going brown. They tend to degrade gracefully and slowly, making the reduction in performance less obvious. The solution to this problem is to incorporate the more recent data into the neural network. So one way to do that is obviously to just take the same neural network back to the training mode and start feeding it additional new data. Another approach you might take is to simply start all over again by adding new examples to the existing training set and training an entirely new network, perhaps even with a different topology. So neural networks consist of basic units that mimic in a very simplified fashion the behavior of biological neurons. It's been claimed, for example, that there is a unit within the visual system of a frog that fires in response to a fly-like movements, and there is another unit that fires in response to things about the size of the fly. Now, these two units are connected to a neuron that fires when the combined value of these two inputs is high. And this neuron is an input into yet another, which triggers the tongue flickering behavior to capture that fly. So here's an example. Two examples, actually, of course. A simple neural network, in this case, takes 4 inputs and produces an output. The result of the training this network is equivalent to a statistical technique called Lagrangian regression. Now the second network, you see below it, this has a middle layer, which we call the hidden layer, which makes the network more powerful by enabling it to recognize more and more patterns. And the more hidden layers we have, the more complex the network can become. Increasing the size of that hidden layer makes the network more powerful, but it introduces the risk of overfitting. Usually I've found only one hidden layer is needed. But a neural network can produce multiple output values as well. A feed-forward network, also called a multi-layer perceptron, NMLP in KNIME, are the simplest and most useful type of network direct modeling that you use today. There are three basic questions to ask about them. What are the units and how do they behave? That is, what is the activation function? How are the units connected together? And that is, what is the topology of the network? And then the third is, how does the network learn to recognize patterns? That is what backward propagation and more generally, how is the network trained? The answer to these questions provide the background for understanding the basic neural networks. The unit combines its inputs into a single value, which is then transformed to produce the output. So these together, these units, are called an activation function. When combined reach the threshold, the unit is activated and the output is high, like a biological counterpart you saw with the frog. The unit in the neural network has the property that small changes in the inputs, when combined with values within the middle range, can have relatively large effects on the output. Conversely, when large values in the input may have little effect on the output. And when combined with inputs from the middle range, the property where sometimes small changes matter and sometimes they do not is an example of nonlinear behavior. So the activation function in a neural network has two parts. The first part is a combination function, which merges all the inputs into a single value. The most combination function is the weighted sum, where each input is multiplied by its weight and these products are added together. Although the functions, there's a lot of flexibility with the choice of combination functions, the standard weighted sum works well for most cases. The second function is the transfer function, which gets its name from the fact that it transfers the value of the combination function to the output unit. So the combination function and the transfer function together constitute the activation function. The result is one output value, usually between -1 and 1. The transfer function calculates the output value from the result of the combination function. And then the combination function combines all the inputs into a single value, and it's usually with weighted summation. And then each input has its own weight, plus there is an additional weight called the bias. Now our real estate example shows here provides the input into the feed-forward neural network and illustrates that a network is filled with seemingly meaningless weights. A feed-forward neural network calculates output values from the input values. The topology or structure of this network is typical of networks used for prediction and classification. The units are organized into 3 layers. The layer of the left is connected to the inputs and called the input layer. Each unit in the input layer is corrected to exactly one source field, which has typically been mapped to the range of -1 to 1. The support layer represents the processes for mapping values onto a reasonable range. The next layer is called the hidden layer because it is connected neither to the inputs nor to the output of the network. Each unit in the hidden layer is typically fully connected to all the units in the input layer. Since this network contains standard units, The units in the hidden layer calculated their output by multiplying the value of each input by its corresponding weight and adding these up and applying the transfer function. So a neural network can have any number of hidden layers, but in general one is sufficient. The wider the layer is, that is, the more units it contains, the greater the capacity of the network to recognize patterns. This greater capacity has a drawback. We want the network to generalize on the training set, not memorize it. So the hidden layers should not be too wide. Each unit also contains a constant input, sometimes called a bias, and it has a value set to like 1. Like other inputs, it has a weight and is also included in the combination function. The bias acts as a global offset to help the network better understand patterns. The training phase adjusts the weights of the constant inputs as it does on other weights within the network. The last unit on the right is the output layer, because it is connected to the output of the neural network. It's fully connected to all of the units in the hidden layer. Most of the time, the neural network is being used to calculate a single value, so there is only one unit in the output layer and that value. We have to map this value back to understand the output. It is possible for the output layer to have more than one unit. For instance, the department store chain wants to predict the likelihood that customers will purchase products from various departments, such as women's apparel, furniture, and entertainment. The stores want to use the information to plan promotions and direct target marketings. So how large should that hidden data be? The real answer is that nobody knows. It depends on the data, the patterns being detected, and the type of network. Since overfitting is a major concern with networks using customer data, we generally do not use hidden layers larger than the number of inputs. So a good place to start with many problems is to experiment with 1, 2, or 3 nodes in the hidden layer. The number of features, the variable selection problem, is a common one among statisticians. In practice, we find that decision trees provide a good method for choosing the best variables. By connecting a neural network to a decision tree node, the neural network can use the variables chosen by the decision tree as having the highest coefficients. As an alternative method, you could start with a handful of powerful variables that make sense, and then experiment by using other variables to see which ones improve the model. Typically, a minimum number of a few hundred examples are needed to support each feature with adequate coverage. Now, some features take on continuous values, generally ranging between a known minimum and maximum bounds. Examples like dollar amounts, monthly balance, sales income, and so on. Averages, ratios, and physical measurements, they're all going to be features with continuous variables. So a feature with a continuous value that falls between a specific range, like a minimum and maximum, can be scaled to the reasonable range we're looking for of -1 to 1, using a calculation such as the map value equals 2 times the original value minus the min divided by the maximum value minus the min plus 1 minus 1. The normalized function will be much easier to use in this particular case, however. Features with ordered or discrete values are slightly different. Like continuous variables, they have a maximum and a minimum range, for instance, usually from like 0 to 100, but the exact range may depend on the data being used, or the number of children may go, for example, from 0 to 4, with anything over 4 considered to be a 4. So preparing those kind of fields is simple. First, count the number of different values assigned to each proportional fraction of some range, say 0 to 1. For example, if there are 5 distinct values, then these would get mapped to 0, 0.25, 0.5, etc. Notice that the mapping values into the input interval preserve the ordering, and that's an important aspect of this method to preserve information not being lost. So in this example, we can see how I would map the number of children to a value of no children, 1 child, 2, 3, 4, or more, and each one of them get mapped to 1/4 of that range. Now, there are 3 ways we can deal with categorical variables. The first is to treat the codes as discrete ordered values, mapping them using the methods discussed in previous slides. The second way of handling categorical features is to break the categories into flags, 1 for each value. This is my preferred method. So with male, female, and unknown, I would have 3 new columns: male, yes or no; female, yes or no; unknown, yes or no, and those values would be mutually exclusive. The third is to replace the code itself with the numerical data about the code. Instead of including zip code in a model, for instance, include various census fields, such as the median income or the portion of household with children, something like that. The reason I prefer the flag approach to assigning numbers is really very simple. When working with categorical variables in neural networks, you have to be very careful that when mapping them to numbers, that the mapping doesn't introduce an ordering of the variables which neural networks take into account, even if the ordering doesn't make sense. So given a male a 1, female a 2, and an unknown of 3 is going to make the unknown value get weighted higher because the number is higher, even though that number was just randomly chosen. Should your data have any date-time data, you're going to want to handle that separately. Because any date and time can be represented as a number of days or seconds since a fixed point in time, allowing them to basically be mapped out and feed directly into the network. And that's going to be the preferred method. And thankfully, KNIME has nodes that support that automatic conversion. Now, when you're interpreting the results of a neural network, especially when it comes to prediction values, neural networks take the work of interpreting the results. When estimating continuous value, often the output needs to be scaled back to the correct range. For instance, the network might use to calculate the value of a house, and in the training data set, the value is set from so that, for example, 303,000 maps to -1 and 250,000 maps to +1. If the model is later applied to other houses and the output is 0, then we can't figure out what that actually represents, the 176,500, halfway between the max and min. So the inverse transformation makes neural networks particularly easy to use for estimating continuous values. In our case, we use the normalizer function, and at the end of the model, we use the denormalizer function to put it back. For binary or categorical output variables, the approach is still to take the inverse of the transformation used for training the network. So if churn is given a value of 1 and no churn is given a value of -1, then values near 1 represent churn, and those near -1 represent no churn. And you'd write sort of an if-then-else column expression node to handle that. If the original training set had 10% churn, then the cutoff would be reasonably set to -0.8 rather than 0, the halfway point. So the output of the network does look like the probability in this case. However, the probability depends on the distribution of the output variable in the training set. Neural networks are opaque. even knowing all the weights of the nodes throughout the network really doesn't give you much insight into why the network produces the results that it has. And it's that lack of understanding that has some appeal and some drawback. After all, we don't understand the human consciousness arises from the neurons in our brain. But as a practical matter, though, consequence or opaqueness impairs our ability to understand the results produced by the trained network. So, unfortunately, the same nonlinear characteristics of neural network nodes that makes them so powerful also makes them unable to produce simple rules. So, a technique called sensitivity analysis can be used to get an idea of how opaque models work. Sensitivity analysis does not provide explicit rules, but it does indicate the relative importance of the inputs in the result of the network. So sensitivity analysis uses the test set to determine how sensitive the input of the network is to each input variable or feature. Sensitivity analysis uses the test set to determine how sensitive the output of the network is to each input. The following are basic steps for sensitivity analysis. Find the average value for each input. We can think of the average value as the center of the test set. Then measure the output of the network when all inputs are set to their average. And then measure the output of the network when each input method is modified, one at a time and at the minimum and maximum values. That will give you an idea of how each attribute is impacting the model. Now, in sensitive analysis, for some inputs, the output of the network changes very little for the three values, min, average, and maximum. The network is not sensitive to these inputs, or at least when all the other inputs are put in together. Other inputs have a large effect on the output of the network. The network is sensitive to these inputs and sensitivity of the network for each input. Using the measures for all of the inputs contains a score of relative measures of the importance of each feature. Really, it's providing you another way of finding and identifying the coefficient of each feature. All right. I'm continuing to use our sample data set from all the prior chapters. So if this is the first presentation you're jumping into, look back at some of the other presentations to see the data in more detail. But I'm going to show you just right now the file table to remind you that at the end of the day, we are trying to predict opportunity result. Is this sales that we attempted to win or a loss based on a number of individual data elements and some categorical data? So as described, I'm going to use the normalizer feature, and I'm going to train this network, and I'm going to have a minimum value of 0 up to 1, and just using the minimization formula. And I've taken all numeric fields and put it in there. Now, my one-to-many, I'm leaving opportunity result alone as a win or a loss. All the other categorical variables have been converted over to a series of yes-no flags. And as important is, and then I've removed the individual input columns to say I'm only keeping the values that have been converted over to yes-no flags in the form of binary 1-0s. Now I do my standard partitioning of 70% of the data and 30% of the data for training the model. And in my predictor here, I've got the maximum number of iterations, the number of times I'm willing to go through the loop, and I can specify the number of hidden layers. I'm generally going to start this with 1, and the number of neurons in that hidden layer, setting at 10. I've set the predictive class column to be the opportunity result. I can tell it to ignore individual missing values, And I can use a seed randomization. This, again, like we've spoken before, allows me to repeat this same model over and over again if I need to for testing purposes. Then the prediction does nothing more than, again, like all the others do, ask for the name of the column you want to predict and append the column distribution codes as part of the output. And then finally the scorer node. Now, remind you, I'm not going to walk through how to read the accuracy statistics in great detail here. I'm simply going to tell you that if you need a refresher, go back to chapter 59 on decision trees, where we spent about 30 minutes talking about the scorer and how to interpret all of those fields. So for right now, I'll assume that you've taken that portion of the class already and you're comfortable reading a confusion matrix and the accuracy statistics. So let's look at the accuracy, in this case, of my neural network. Well, on the sensitivity, my ability to detect winds is at 59%, almost 60 if I round, and losses are at 93. So overall, my model accuracy is 0.863, 86%. It's not doing too bad, but of course, it's not matching up to what we saw in Random Forest in terms of overall productivity. So I wouldn't probably likely do much more with this. If I wanted to, I could set some parameter optimization loops to loop through and see if I could tweak the model to get it to perform a little better. But for purposes of this class, I think I've done enough to exclude it. So again, I can see the results of each of my, as I'm doing all the comparisons of all my various models that I built, starting with the trees. And I've now updated to include our neural network and its results, and it still hasn't knocked off the Random Forest solution, but it's still a very good solution. So let's review the chapter. In neural networks, the modeling of the neural network connections in the human brain is similar to that from data from past experience. And internal weights are difficult to understand. So the structure of the model, the base elements of the neural networks are the input nodes and the output nodes and the hidden layer. The activation, you've got two functions for each neuron. You've got a combination function that merges all the inputs into a single value, and then the transfer function that moves the value of that combination function into the output. That completes this chapter of the class. Feel free to move on to the next chapter.